Hello, my name is Rabia Sagheer and I am an MS Mathematics student at the Institute of Business Administration, Karachi, Pakistan. My topic is categorification of multi-parameter persistent homology. Here is the pipeline. We have data. We use some construction to define multi-filtration, use some tools to define multi-parameter persistent modules for these multi-filtration, define metric on them, and then prove the stability of modules. Or we can define some invariants such as signed barcode or fiber barcode, and then we can prove the stability of these invariants as well. So this is the non-categorical definition of multifiltration. We have a partially ordered set P, which is given by P1 times to Pn, where Pi is the totally ordered set. And a multifiltration over this partially ordered set is the collection of topological spaces such that whenever x is less than equal to y in partially ordered set, we have f of x to be the subspace of f of y. So now how to categorify this definition? The favorite thing for category theorists is whenever they see any mathematical thing, they try to define it or try to see it as a functor. The same thing is done for multifiltration. We define multifiltration, a p-index multifiltration to be a functor from P to the category top. This top is the category of topological spaces and continuous maps. And P is the same as the partial order set, but now we are treating it as a category. So whenever we have a morphism in this category P, that is whenever x is less than equal to y in P, we would have this f would map this morphism x less than equal to y to the inclusion map. That is, we would have an inclusion map between f of x and f of y. So these two definitions are same. We are just using now a different framework, which is a categorical framework. So here is an example of bifiltration. Now our partially ordered set is n times n to the category top of topological spaces and continuous map. So this is how a commutative diagram of it look like. So for example, as you know that 0, 2 is less than 1, 2, we have a inclusion map between the topological space f of 0, 2 and f of 1, 2. So the intuitive idea of this commutative diagram can be seen by this bifiltration of our um, triangle or two simplex, and as you can see k1 2 is the subcomplex of k2 2. Now we will define multiparameter persistent modules. So for a fixed field k, we then again take a partially ordered set, and we define a multiparameter persistent module over this partially ordered set to be the family of vector spaces, and these vector spaces have linear maps between them such that we translate our reflexivity in the partial ordered set to be the identity map um, between the vector space, and also we translate the transitivity in this partial order set to be the composition between the linear maps. Now the categorification of this definition is done the same way as for multifiltration. We define our multiparameter persistent module to be a functor from P to the category vect, where vect is the category of k vector spaces and linear maps. So now I would not define these two conditions as I defined them in the above definition, because when I say a functor, these two condition holds. So now what else we can do? We can make a category for these multiparameter persistent module for these functors. So for fixed P, the P-index persistent module form a category of functors whose objects are persistent modules, P-index persistent modules, and the morphisms are natural transformation. So as we know that whenever x is less than equal to y, we would have a linear map from mx to my and nx to ny. But the morphism between two persistent module, let's say it is eta from m to n, this eta is the collection of linear maps such that for each x in P, there would be a map between mx and ny. So all of this eta is the collection of all the annexes for all the x belongs to p. So for example, we can see this n index persistent modules, and the morphism between them is given by this commutative diagram. So category of persistent modules is actually the abelian category. I will not define formally what is abelian category, but abelian category has byproducts, has zero objects, and every morphism in abelian category has kernel and co-kernels. So since our category of persistent module is the abelian category, every morphism, let's say eta, between two persistent module can be decomposed like this, or can be written like this, where kernel of eta, image of eta, and co-kernel of eta is actually the also p-index persistent modules, multiparameter persistent modules. So we will again see our previous example in which we had an index persistent module. So kernel of eta would have a morphism, and that morphism would be the collection of all these vertical maps. And we can also define a zero object, and this zero object would also be a p-index persistent module. It will take every element of p, and and the image of that x would be the zero vector space. So we can use category of persistent modules to define or to prove some abstract theorems, or maybe use them to define some further things. I can, for motivation, I can show you a proposition. This is a very popular one, that the category vect zn, that is category of persistent module indexed by zn, is equivalent to the category of modules. So in other words, our p-indexed functor here can be seen as the module. That is why the name is also persistent modules. So now we have defined the persistent modules as a functor. We have also defined its category. But what is the relationship of filtration and multi-parameter persistent modules? So what do? We take the filtration, and on every topological space and every inclusion map, we apply homology functor, and we get a persistent module. So for example, here we see this P2 top is actually the filtration. We define for every simply shell complex, we will define a chain complex. For every inclusion map, we will define a chain map, and then we will compute the homology. And we know that homology gives us the result in category of vector spaces. So simply we write our homology functor, ith homology functor, from P to the category of vect, and this is also actually the persistent module. So for example, here this is the commutative diagram of zeroth homology. As you can see, this k2 comma 3 has two connected components. So we have k square here, where k is the field. So you have to know all of the background work being done here, and once you know all of the background work, you can then simply treat your homology as a functor. So now, having defined the multi-parameter persistent modules, we will define our distance notion between them. We have two definitions, shift functor and transition morphism. Due to the shortage of time, I will explain these two definitions by this commutative diagram. So what does shift functor does is it takes ms and it maps it to ms plus epsilon, and also it shifts also all the linear maps itself. And what is a transition morphism? Transition morphism is the morphism between ms and the shifted version of it. For example, that is the morphism between ms and ms plus epsilon. So now, to define the interleavings, we use these two definitions. So we say two persistent modules m and n are epsilon interleave if there exists a morphism eta m to n epsilon and eta dash m to n epsilon, m epsilon, sorry, such that they hold these two equalities. So precisely what does this mean? It means, for example, if I have z index module, then one interleaving would be from m0 to n1, it will shift the functor m0 to n1, and then it will shift n1 to m2, and then it will make the it will have a transition morphism from m0 to m2. So this is the interleaving distance. So this epsilon interleaving uses shift functor and transition morphism to define epsilon interleaving between two persistent modules. Having defined the epsilon interleavings, we can then take the infimum of all such interleavings, and we can define the interleaving distance to be the infimum of all those epsilons. Now, since we have defined our distance in terms of categorical framework, we can use this distance to prove stability theorem. For example, the interleaving distance di is stable for all topological spaces. We can also take two data sets, make a construction for filtration, and also prove the stability of that filtration. For example, here are two results for multi-cover bifiltration and subdivision rips bifiltration. So that's all from my side. I hope you learned something from this video. Thank you.